Monica, you go swimming. Stay in, take a shower too long, whatever the case may be. What starts happening to your wash dishes, good. All right, that's probably a better one. It happens to your fingers. Why? All right. What's going on there? Anybody? She's washing dishes. Is water going into her hand, or is water going out of her hand? All right. The only way I can keep this straight is that nature says things flow from what concentration to what concentration? High to low. Okay. So what you have to do is look at the finger and look at the water outside the finger. Right? So this is the dishwater. Washing all these dishes, and then here's the finger. Where is the water more concentrated? Is it in the finger or is it in the dishwater? It's the dishwater by far. I mean, I know it's dirty and there's soap and all this stuff, but your finger, look at all that. It's got fleshy stuff. It's got cartilage. It's got blood. It's mostly water, but there's a lot of other stuff in there. Water's more concentrated in this dishwater. So that means water is actually flowing into her hand. That's why it's getting all puffy looking, right? She gained weight washing dishes. Technically, right? But you just as well drank water. It's the same thing. It's not. Okay. So that's what's going on there. You can, this takes a long time, but you can actually fix wilted lettuce. Takes 3 hours, though. So what'd they put it in? Water. Okay. So I always thought it was kind of gross in the, in H-E-B and all of these grocery stores. They're constantly spraying water over everything. Yeah, thinking that's all kind of germy and stuff. It just seems that way to me. But now you know why. Keep everything wet, because then it won't wilt on you, right? I can't submerge it, so they're just continually shining, that mist water on there. Now this is kind of nasty. It's not a very nice thing to do, Jasmine. No way, you did? Let's move the question to Summer then. Summer, what did you do?
I used to pour salt on the snails, watch them bubble.
Did you hear that? Yeah, oh, what a horrible way to go. Why would a snail start bubbling if you dump salt on them? Yeah, your water's going one way or the other. Which way is the water going? Is it going? It has to go from high to low. So now you dump all this salt on that snail. It's really very, very, very salty water. It's pretty much saturated. So the concentration of water is actually higher inside the snail. You're right. So it's going out. It's drying it out. It's desiccating it. You're right. Okay, and slimy. All right. Osmotic pressure. Okay, let's take a look at an animation on osmotic pressure.
When two solutions with the same solvent are separated by a semi-permeable membrane, solvent molecules migrate through the membrane from the solution of low concentration to the solution of high concentration. A concentrated glucose solution is added to an inverted funnel with a semi-permeable membrane, and the funnel is placed in a beaker of pure water. Water flows from the beaker into the funnel. The upward flow of solvent stops when the pressure of the solution above the membrane equals the osmotic pressure, pi.
Okay, there's some funky stuff going on in there. Let's take a look at this. Now, they said that there's solvent molecules on both sides, Cassandra, of this membrane. What are the solvent molecules being represented as? Yeah, what are they using to represent the solvent molecules? It's supposed to be water, but what are they using to represent the water molecules? You want to see what I'm driving at? They're using the little, those blue dots, right? These are the water molecules, right? And then both sides of this container are separated by, Eric, what type of membrane? A permeable membrane. Well, semi-permeable membrane. Not everything can permeate through it. In fact, AJ, only what can go through this semi-permeable membrane? Only water can. He's right. Jessica, why is that? You got some other stuff in there. You have glucose, big sugar molecules, but why can't they pass from one side to the other? They're too dang big. Exactly. That's all a semi-permeable membrane is. It's just something, little tiny holes or gaps. So only very small molecules can get through. So a semi-permeable membrane would not be very semi-permeable if the solute was very tiny, like a gas or something. It's not going to work. Okay. So you've got solvent on both sides. Which side, Alyssa, right? The left or the right, yeah, has more concentrated water? Which side is there more? Could you say the water is actually more concentrated, more mass per unit volume of water? It'd be the left, yeah. Because look, there's glucose is taking up some space, some volume over here. So yeah, there's higher concentration on that side. Hey, Mari, what does water actually have a concentration? I think when we describe concentration, you say big M. What did that stand for? You want to remember? Molarity. Does water have a molarity? Pure water, Mari. Does it? Yeah. Why not? All this is the number of moles over the number of liters, right? So take the number of moles of water present in a certain volume, divide the two, and you're going to get 55.4. I don't know if it really matters, but pure water is 55.4 molar. Okay. Okay, so this is going on. And then, Summer, is water going in both directions here? In other words, is it going from left to right and from right to left? Or is it only one way?
It looked like it was just going to one side.
Yeah, the animation only showed it one way. But can you stop it? Can you stop it going this way? No, it's just a little hole. If it goes through the hole, it goes through the hole. The thing is, though, the rate is higher going in which direction? The rate is much higher going this way. Okay, so water keeps going in this direction, piling up in there, right? The level of the water gets
And the funnel is
higher and higher and higher and higher and higher. Then they said, it stops. The level stops. In other words, all that's happening now is the rate going backward, going through this, right, is the same, right? The rate of water going in and the rate of water going out is the same. So somehow this rate got big enough to match it, to match the pure. And it's bigger because there's a bigger pressure in here now. How is there pressure in here? Pressure from what? Gravity. Look at the weight of this thing, right? As this gets higher and higher and higher, there's just more stuff. So the pressure on that membrane gets higher and higher and higher as this column gets up. Well, yeah, so if the pressure gets higher and higher and higher, you're just going to be pushing more water through. So sooner or later, those rates are going to be the same, and then the level's going to stop. So that pressure where the rate, where the rates become the same, is called the what pressure? It starts with an O. Osmotic pressure. Okay, that's kind of what we're playing around with. Okay. So here's our equation for osmotic pressure. Now the osmotic pressure, that's what symbol? That's pi, yeah. Right, Caroline, that's pi. I want to see if we can get units for all this stuff. But I want to start you out, Caroline, because I know the trick in doing this. What's big R? What is big R? We saw it once before in the 0.0821 thing. It's that in the ideal gas law, that big R, the gas constant. Okay, it's the 0.0821. Now let's see if Caroline remembers its units. I give you this stuff, but let's just, you used it probably 250 times. There's an ATM in it. There's a liter, there's a Kelvin, and there's a mole. Okay, that is a big hint on what this other stuff is. So Vanessa, for example, that pi had better, this osmotic pressure had better be in what units for pressure? What units of pressure? It has to, look at the big R, it has to be in ATMs. And I'll bet you anything, this homework questions, they're going to say, oh, the osmotic pressure is 2.85, not ATMs, what? Millimeters of mercury, right? You know they're going to do that. So you got to convert to ATMs. And I gave you the conversion, but yeah, see, someone remembers this stuff. 760 in an atmosphere. So 760 millimeters of mercury in an atmosphere. Okay, so we know the units of osmotic pressure have to be atmosphere. How about that big T, Albert? Temperature in units of Kelvin. They're going to give it to you in Celsius, I'm sure. How do you get to Kelvin again, Lauren? How do you get to Kelvin again? They give it to you in Celsius. Add 273. Okay, so no big deal. Victoria, we have one left. Big M. Molarity. Molarity. Okay. Now, I'd give you definitions, Monica, of all these concentrations, but what was molarity again? Do you remember? No, that's molar mass. Moles of solute all over. No, that's molality. Liters. That was big M. Okay. So I don't know how many class periods back this was. We did problems like this. Over liters of solution. Remember that? And we treated it like an algebraic equation. And Jasmine, there's how many variables in that equation? How many variables in this equation? 3. And they always gave you 2 and you solve for the third one. Right? Okay. It's going to be the exact same thing. Except they're going to ask for what? Do you see this coming? They're going to ask for MWT. Molecular weight. And what are the units for it? Grams over moles. Do you see where this is coming from? Or see where this is going? We need to get big M. The problems are always going to ask this one. I'm just showing you the big picture. The problems ask or want probably sounds better. Or find, right? Find. There's so many problems that say find the molecular weight. Why? Because this is such an osmotic pressure and all. Osmotic pressure is actually easier than this boiling point and freezing point stuff because all you do is stick a little tube and measure the level and stuff. It's so much easier. So to find molecular weight, they're going to use osmotic pressure a lot. So you have to find molecular weight, and they always give you the number of grams of solute. We dumped in so many grams of solute, and then they found the osmotic pressure and things. You get that mole all the way from up here, right? You know, that's how it's going to work. They're going to ask for molecular weight, so that means and they give you the grams, you just have to find the moles. Well, to find the moles, you got to find big M. But to find big M, you have to, right, use the osmotic pressure equation. Make sense? That's the big picture. Okay, Cassandra, I see one more complication before we move on. I see two osmotic pressure equations. I see two boiling point and elevation equations. You know, it just keeps on going. Why? What's going on there? Summer pretty much asked you the question, and you're wondering it. What does the what stand for? The I. Eric knows. Nope. Good guess. You're close. I don't know if you remember. It was kind of a mute point, but I said that last class period we were using all the equations minus osmotic pressure in the left-hand side. And it couldn't be ions. It had to be molecules. Because if it's ions, the effect just gets quadrupled or tripled or whatever. It just depends on the number of ions. You get twice as an effect. If you have sodium chloride, for example, little I would be 2, because you have 2 ions. And so you'd have to use this side of the equation. For example, let's say the solute is barium chloride. Who knows? You can throw in all the other English. Make it a freezing point depression question. I don't care. But if this is your solute, barium chloride, definitely not a molecule because you see a what? A metal. So definitely not a molecule. It's an ionic compound. That means you have to use this set of equations, and your little I has to be what? 3. The number of ions, 3. Right? Because that breaks up into a barium and 2 chlorides. So it's 3 ions. So little I is 3. And that's the game we're going to be playing. Okay. So we'll do a bunch of those. And I'm not sure why they threw this in, but we'll just show you quick here. Colloids. I think it's a technicality, and maybe that's why they're showing you. We like to, all this stuff is supposed to be for solutions, and a solution is supposed to be homogeneous. Remember that word? Same throughout. Well, there's some compounds where they're really not true solutions. They're really different throughout. And you can kind of tell by shine a laser through. If you shine a laser through something that's the same throughout, right, you can't even see anything, right? You can see the water. You can't see the water. I don't know, maybe you can kind of see some dust or little bubbles. I'm trying to see if you can see the laser going through the water, right? It's pretty hard to do. But if I make a colloidal solution, so I need some really big molecules in water and disperse them. Okay, what I'm doing is I'm just dumping some dried milk, some coffee mate, really big globule or fat molecules in here. Stir them up. All right? It looks the same. All right? It looks like a solution, but technically it's a colloidal suspension. Look at that. You see the red line definitely going through there. That's a Tyndall effect. This really isn't a solution. It's a suspension or something. These big hunkin' big blobs of fat are just suspended in the water, hydrated somehow, I don't know. But it's not, the word really isn't solution. So they call it the Tyndall effect. Okay. No big deal. Let's see if we can work some of these problems out. An aqueous solution contains 0.296 grams of a polymeric. Now, it'll be helpful to know what that means. A polymer. You heard of polymer? Big, big, big molecules. Think of an analogous analogy would be a train, right? You have a chemical compound, chemical bondage to another chemical compound. They're just identical, and they just go on forever. I mean, their molar masses are like 50,000 grams per mole. They're just huge. So, because the reason I'm telling you that is because, look, they want you to find molecular weight. So when you get a huge answer, that's right, because it's a polymer. Okay, so we have 0.296 grams of a polymeric unknown. There's 125 mils of solution, temperature is 25. Osmotic pressure, 2.58 millimeters of mercury. What is the molecular weight of the unknown? So let's see if Brandy can get us started on this. What would you do? What would you do first? Oh, that's a good one. Because and the reason why is because you're looking at what equation, Brandy? Probably going to end up using what? Yeah, the first one, pi equals MRT. Yeah. Okay. So let's do it. She wants to get the temperature in Kelvin. You know where you're going to need it. 25 plus 273, 298 Kelvin. Okay, we got that one. Jessica, we're after molecular weight. What could you do next? We may not be doing this in the logical order, but we'll get there. Right. Molecular weight is what over what? Grams over moles. This is where I would have started. But I know there's a strong urge just to start working the problem out. But if you started out this way, it's healthier because it kind of guides your efforts. But maybe not. It helps me. We're going to need it, Alyssa. We're going to need what Jessica just mentioned because that is our final answer. Okay, what could you do now? What's that? Okay, our R, we're going to need that. Our R is 0.0821. Liter atmosphere, mole. We're going to need that for sure. Okay. Mari, what else could we do now? Oh, yeah, that convert those millimeters of mercury, that osmotic pressure. 2.58 millimeters of mercury. And there's 760 in atmosphere. Definitely going to need that. 2.58 divided by 760. About 3.39 times 10 to the negative 3. Okay. Summer, now what? Oh, yeah. What are the grams? The grams are what? Yeah. We're halfway there to molar mass because this is the 0.296. Okay. Caroline. Now what could you do? We got to get that bottom part. We got to get that moles. What could you do? Anyone have an idea? AJ? Use the molarity. Moles over liters. Exactly. That's how we're going to get it. You said that big M is moles over liters. And whatever you get for that, right, it's right here. Okay? You got a good game plan there, Vanessa. How are you going to use it?
They gave us the 125 milliliters. We can convert that.
Oh, yeah, convert that into liters. Okay. I guess I can go this thing. That should be 0.125 liters, right? 125 milliliters. There's 1,000 milliliters in a liter. Divided by 1,000. So all we're missing is that big M. Yeah, there it is. Here it is right here. Find that big M. And put them in. We'll solve for our moles. And once you get it, put it in the molar mass. Okay, so we already did all the nice converting. Make sure you put in the right units for stuff. We've got the pi equals mRT. Pi is the 3.39 times 10 to the negative 3. M is what we're trying to find. R is 0.0821. And T is my 298. Now, I don't know, it might be bad habit, but I don't like to put the units in down here. The reason why, it seems redundant. Because we did all this nice little converting up here to make sure everything's in the right units. And it's a lot easier to handle things. I think it's cleaner to see, too, if you leave it like this. But that's up to you. Albert, how are you going to solve for big M? What are you going to do? Yeah, take.
Divided by the point.
Yeah, and then.
Divided by 2.
Yeah, you see how he's doing that? Just take the 3.39 times 10 to the negative 3, divide it by the 0.0821, divide it by the 298, you'll have it. And did anybody get an answer? 1.39 times 10 to the negative 4, a couple of folks got. Okay. Now we're ready to big M has to be moles over liters. 1.39 times 10 to the negative 4 has to equal moles. 0.125. Remember the trick to doing that? Kind of like the diagonal story. Yeah, I get rid of the 0.125, so it has to go up on top. So take it times. Did you get about 4.24 times 10 to the negative 4 for the moles? Does that look good? If that's what we got for the moles, anybody else get that? Yeah? Oh. So it should be 1.39 to 10 to the negative 4 times 0.125, right? Wow, everyone else is getting something different. What did you get? Everyone got the same thing, but me. 1.7. Sound about right? All right. I don't know what I did. Okay. Now we have to find molecular weight. We have it. I think it was 0.296. Yeah, the 0.296 grams all over 1.74 times 10 to the negative 5 moles. And we'll get so many grams per mole. That's our answer. Holy cow, around 17,000 or so? Somewhere around there. And it should be big because of the word what up here? Polymeric. So I expect a big molar mass. Okay? Yeah, and grams per mole is molar mass. So I think it always works this way. To find number of moles, if it's not big M molarity, it's going to be little cm to get your moles, right? And either way, it'll be a very similar type of problem. Okay, let's try this one. In a mountainous location, the boiling point of pure water is found to be 95 degrees. Remember that? Those guys up in Denver, they can't get the water as hot because it's elevated, the atmospheric pressure is not so high. So they can only boil their water at 95. But, hey, I want to boil my water at 100. You know? So fine. The cheapest way to do it is to dump some salt in there because salt's the cheapest thing you can find. Right? Okay. So how many grams of salt do you have to add to pretty much a bucket of water, that's about 1 kilogram, to bring the boiling point up to 100, where water boils for us? That's the question. Okay, Lauren, where would you like to start on something like this?
Like, where would I start first?
Yeah, I don't.
Sure would be the easiest.
Gotta start somewhere.
The
The what?
temp,
The temp?
right? It's working on the last one.
Yeah. Well, see, if you start changing temperatures to Kelvin, you be careful. Start with the equation that you're going to use. Because in some of those equations, they wanted a temperature in Celsius. Right? See what I'm getting at?
Yeah.
Which one would we be using? For this question, the boiling point one. Now, she has two choices. Which one is it going to be? The one with the I. Because we're messing with an ionic compound. Delta TB equals I KB CM. Okay. Good starting point. Victoria, now what?
Start by putting the best of those pictures.
Okay. That delta TB is going to be what? 100 minus 95. Did you catch that? She says that delta TB is just 5. It's a change in the boiling point. And she just took this one minus that one. Exactly. It's exactly what that delta T is. Okay? Monica, now what? Okay, let's find the CM. So that means we need an I and a KB. I'll give a, here, it's Monica. I'll give you back your quiz. KB's on there, I think. Right, for water? 0.512. 0.512 is my KB. And my little I, everybody's got to be what? It's got to be 2, because it's sodium chloride. It breaks up into sodium ion and chloride anion. So that has to be 2. So I'll solve for my CM. Okay. 5 divided by 2 divided by 0.512. 4.88. Okay. Hopefully that helped, Jasmine. What now? Yeah. We're after that grams of sodium chloride somehow. Right? We're after that. What's that? use the molality equation. And in the molality equation, and I give you these, you just copy them down. Moles of solute all over kilograms of solvent. Now, what's key is you don't see grams of sodium chloride in there, but you do see what? Yeah. Yeah. I mean, what I'm saying is your answer is in there. It's not in grams, though. It's in moles. Remember, if you're given moles of something, you can easily get grams. You just use what? What is it called? Molar mass. Molar mass. If you're given grams of something, you can calculate moles. Just use molar mass, right? So grams and moles are always really easily interchangeable. And I think that's one thing you just need to get used to seeing, right? When you see moles of something, my brain doesn't see moles. My brain sees moles and grams at the same time because I know they're exactly the same thing. So when I see the CM equation, I see grams of sodium chloride. And that's what I'd like to see if you can work into. And just get used to, oh yeah, it's just molar mass. So if I know moles, I know grams. If I know grams, I know moles. They're just interchangeable. So that's how we're going to get it. So let's solve for it then. We'll have 4.88. We'll have our moles up here. We need kilograms of solvent, though. Cassandra, what is that going to be? 1. Yeah, it just says 1 kilogram of water. Well, that math was easy. All right? So my moles is going to be 4.88. Okay, Eric, how do I get to grams now? Couldn't hear what he said. 4.88 moles. I don't know. What's the molar mass of sodium chloride? What did you say it was? 58.5. So do you see how he got it? He added up the molar mass of sodium, added that to chlorine, and he got 58.5. And you write it this way, otherwise the moles won't cancel. Sounds like it's going to be a lot of salt to dump in there to get your boiling point up. I think I just boil it longer. 4.88. How much is it? 285 grams of salt. Dang, that's got to be, I don't know, a couple pounds, maybe a pound or so? I don't know. I don't know my grams to ounces very well. But that's a lot. Just to make water boil at 100. I guess it's a lot of water, though. It's a big bucket, but well, not even really that big, a kilogram. Okay. So, oh, we finished. So just keep an eye on these questions, right? Yep. That little I, you use him when the solute is what type of a compound? Ionic. That means you have to have an ion, have to have ions, cation, anion. And you know it's ionic if you see a ionic compound, but a metal, right? You see a metal, it's got to be ionic. Yeah. For example, let's see if you're following. How about if you had calcium sulfate? All right. You really have to remember your polyatomic ions for this to work. Little I is 2, because all you have is calcium, and that big thing is grouped together as sulfate, right? Little I is 2. How about Na3PO4? What's little I? It's 4, yeah, because this is just 1. How about, because you have 3 sodiums and 1 phosphate. So the charge really doesn't matter, you're just counting up the ions. Let's try one more, then we'll call it quits. How about, if you remember this one, you're doing really good. All right, you got the acetate part right. is lithium acetate, and there's just 2. I don't think it's going to get that complicated, but that's it. So come by if you have some questions. We have lab tomorrow.